At a certain temperature, the volume of a gas was V cubic centimeter. What would be the volume if the temperature is doubled? Now, if you look at this question, it is a problem that concerns volume and temperature. You can say that we are required to find the volume for when the temperature is doubled. Clearly, the data given to us in the question fits Charles' law. And so we are going to use Charles' law equation to solve this problem. Let us see the data given to us from the question at a certain temperature. Let us take that as the initial temperature T1. Okay, a certain temperature, so we have T1, initial temperature. I am going to just simply call the initial temperature T1. Is that okay? Because it said a certain temperature. If I want, I can just use any symbol I want, any alphabet I want to represent that T1. They didn't give us the value, alright? We are just told at a certain temperature. Alright, at this certain temperature, the volume of the gas is V cubic centimeter, according to the question. So, I am going to write the initial volume of the gas, as given from the question, is V cubic cm. Alright, what will be the volume? So the final volume now we don't know. V2 we do not know. If the temperature is doubled, T2, the final temperature T2, we are told that if the temperature is doubled, that simply means that the initial temperature will now be twice of its value, okay? So T2 will simply be 2 times the initial temperature T1. So these are the information given to us from this question. And now that we know the details, we can apply Charles' law. Recall, we know that V1 over T1 is equal to V2 over T2. Charles' law. We can still rewrite this equation as V1 over V2 equal to T1 over T2. Let me write it. Or, if you want to arrange the volumes on one side, we can have V1. This V2 will come under like cross multiplying, interchanging V2 position and T1 position this way. So this is over V2, and that will be equal to T1 goes up here, and then over what? T2. One can still write this equation in such a way that the final conditions will be the numerator and the initial conditions will be the denominator. Alright, let us substitute into this equation and see. Our initial volume from the question is V cubic centimeter, so simply V. And so we're going to divide it by initial temperature, and which is T1, because we are told a certain temperature. And that's going to be equal to V2. The final volume we don't know, so we leave it as V2. And then we are dividing it by T2. T2 is twice of the initial temperature, because we are told that the final temperature is doubled, if the temperature is doubled. Okay, so having obtained this, you notice that on the left hand side we have T1, on the right hand side we have T1. The denominator here is simply multiplication, and therefore we can actually cancel T1 and T1 from this equation. But I wouldn't want to do that. I would like to make what we are looking for subject of the formula first, and we are looking for what? V2. Okay, since we are looking for V2, how do I make V2 subject of the formula? Looking for V2, V2 is in fraction form. Simple equation tells us to cross multiply. So we are going to do that. This is going to be V2 times T1, and then equal to 2T1 times V. 2T1 times what? V. Remember, I have done my cross multiplication here. I am looking for what? The value of V2. That is the unknown. Now looking at this equation, V2 has a coefficient. V2 is being multiplied by T1. Simple equation says, according to its principle, to make V2 subject of the formula, and V2 here has a coefficient, we have to divide both sides of this equation by the term multiplying V2. Therefore, I'm going to divide it by T1 and divide it by T1. And so we are going to get V2. If I divide here by T1, dividing here by T1 we cancel out, divide it also by T1. Okay, let me solve the remaining part here. So you notice that T1 and T1 will cancel, T1 will go off. So what do you see here? That V2 is equal to 2 times V. And of course, that becomes the solution of this problem, cubic centimeter. And this actually tells us that what Charles' law said is absolutely correct. When you doubled the initial temperature so as to get the final temperature, you notice that the final volume is twice the initial volume. So you see the trend, the way the thing is moving. Temperature being doubled, final volume is also double of initial volume, telling us that volume is directly proportional to what? Temperature. Alright, let us take another question. The second question reads, at 17 degrees Celsius, a sample of hydrogen gas occupies 125 cubic centimeter and the pressure is 20 millimeter of mercury. Calculate the temperature if the volume becomes 161 cubic centimeter at the pressure of 20 millimeter of mercury. Looking at the question given to us, the information provided tells us that the pressure remains constant. You can see that. Initially, the pressure is 20 millimeter of mercury at a volume of 161 centimeter cube, which you are asked to find the temperature of the gas. The pressure again remained 20 millimeter of mercury. So pressure is constant in this problem, and we are relating temperature to volume once again. And so this is Charles' law. Declaring the data given to us, T1 is equal to 17 degrees Celsius, which of course you have to add 273 to it to convert to Kelvin. 17 degrees Celsius plus 273, okay, 290 Kelvin. Add 17 to 273. Okay, now we proceed. The initial volume under that condition, V1, is equal to 125 cubic centimeter. The pressure is 20 millimeter of mercury, like I said, is constant, so I have no business with that. That simply tells me that this is a Charles' law problem. Okay, calculate the temperature if the volume becomes 161 cubic centimeter. So here we are looking for the final temperature, given that the final volume is 161 cubic cm. So we go T2, we don't know. And then V2, good. Recall that according to Charles, V1 divided by V2 is equal to T1 all over T2. Okay, you can also write it as V1 over T1 equal to V2 over T2. If we substitute the data given to us in this question, V1 is 125, so we fix that. V2 is 161. The initial temperature from the question is 290 Kelvin. Whenever you add 273 to a degree Celsius temperature value, the unit changes to Kelvin. Okay, so T1, 290 Kelvin, T2, we do not know. That's what we are looking for. So we'll leave it as T2. Numerator 290 and then over T2. And so we can now solve for T2. T2 is in fraction form, so you have to cross multiply. If you cross multiply, you have this and this. Now when T2 multiplies 125, you will get 125 T2, and you are looking for T2, the final temperature. Now it has a coefficient, which is 125. So to get T2, you are meant to divide through by the coefficient of T2. What is multiplying T2, which is 125? So what do I mean? Simply, we can make T2 subject to the formula. It's going to be 161 times 290, and then we'll divide it by 125. Let us reach out for a calculator and carry out that arithmetics. 161 times 290 divided by 125. And so it gave me 373.52. So this is the final temperature of the gas in Kelvin. Now note, if maybe you are given the options for this question and it happens that the units of the temperatures are in degrees Celsius, we can actually change from Kelvin to degrees Celsius by subtracting 273 from this Kelvin value. Always remember to solve a problem where you have temperature under gas law. If the value of the temperature is in degrees Celsius, convert it to Kelvin before solving. Now, if the final answer is in degrees Celsius, you can reconvert back. So let me write or T2 can still be 373.52 minus 273. So let us do this subtraction and see what we are going to get. Give us 100.52. This is in degrees Celsius. So you want to take note of what I've just done here. So any one of these is the correct answer to the final temperature of this gas under this condition. Once again, can we actually prove Charles' law in this problem? Let's check. The initial temperature is 17 degrees Celsius, okay? And then the given volume there is 125 cm3. Now notice, the final volume increased because we have 161. So we expect that the final temperature will also do what? Increase from 17 degrees Celsius to a value that is higher than 18 degrees Celsius, which we got 100.52 degrees Celsius. If you also check that of the Kelvin value initially is 290 Kelvin. Since in this problem, the final volume increased and you are dealing with Charles' law, volume is directly proportional to temperature. So the final temperature will also increase. In Kelvin, you saw that you have a value 373.52, which is greater than 290 Kelvin. I hope you enjoyed this video lesson. Please like and subscribe to my YouTube channel, GMAT41. Share these video lessons. If you have a question, please, you can use the comment section. Drop a question and I'll be right there to respond. Also, please share our video lessons. Share the link to your friends, to other scholars, your classmates, and encourage them to visit and subscribe to my YouTube channel, GMAT41. From here, you have so much to learn from different subjects or courses. If you are in Awka, Anambra State, you can do well to contact GMAT41 to join our physical tutorial classes. And especially if you are a Unizik student, Nnamdi Azikiwe University student, you can join our tutorial classes in Awka, Anambra State on campus, alright? I hope to see you in our next video lesson where I'll be teaching you the general gas equation, otherwise known as the combined gas equation. And of course, that will move us into the ideal gas equation. See you in our next class.